Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. And what you're about to see is a pre-recorded training session we did over in the United States. But be assured that a lot of the material that we cover is really applicable to any automotive application. So just be aware that yes, it is a lot of North American vehicles, but they will apply a lot of the same principles apply over in the UK as well. Now, if you do have any questions, if you're watching this during the premiere, you can just leave it in the chat. We'll be monitoring live chat. If you're watching this after the premiere, then just feel free to leave a comment underneath the video and we'll get to those as we can as well. So my name is Jason Gabrenas. I'm one of Snap-on's diagnostic technical trainers. I've been in the training department since 2013, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep at Snap-on, so I had 30 different franchisees I worked with, as well as the shops that they serviced, in order to help everyone get the most out of their diagnostic needs. Then before I did that, it was 8 years at Subaru. So I worked in a dealership, and over time, I guess, just became the default diag guy in the shop. So I always ended up having the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that would come into my bed. Then before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So our topic today is pressure transducer diagnostics. You can diagnose quite a few different systems on a vehicle using pressure transducers. You can test fluids and compression, etc. And we'll talk about a few different examples as we go. But first off, before we even start, we need to talk about the transducer itself, right? Now, there are many different types of transducers on the market. Snap-on has 3 different ones. So Snap-on has 100, 0 to 100 with negative 20 vacuum as well. We have a 0 to 500 and a 0 to 5,000 PSI transducer. So those 3 right there, they come with the cables. And you need to adapt them to the tool as well. So if you have a 4-channel scope, so the old Modus, Veris, or a Zeus, any of those tools, you can use this, what we call a split lead adapter. So this powers and grounds off that funny looking connector on the top of the scope. And then channel 1 and 2 go there. And then we can hook up our transducers over here and an additional accessory port right there. So I could even daisy chain 2 of these together if I wanted to, or if I had something else that plugs into that port, like the RPM pickup, we could run that at the same time as the pressure transducer as well. And then any of our tools with scopes, 2-channel or 4-channel, will work with this over here. We call it the PSA adapter. And that is battery powered. So it doesn't have that special connector. So it works on any of the 2-channel or 4-channel scopes. We got an on-off switch and a place to hook 2 transducers at the same time. So if I were to hook that up to the tool, here's just one example. We have our accessory port there, and we channel 1 and 2. That's the split lead adapter. And then I have pressure probe number 1 right there. You see, I could plug in an additional probe or have that auxiliary port. And then on that PSA adapter, as we call it, it's got a 9-volt battery inside. As I said, we got the switch, transducer 1, transducer 2, and then that grounds to the tool instead of through that accessory port. So we have the black, the red, and the green would give you ground, channel 1, and channel 2. All right, so we have the accessories. If you had an aftermarket or a non-Snap-on branded pressure transducer, let's put it that way, a lot of times you have a BNC adapter. I didn't take a picture of that, but there is a BNC adapter that's available that'll hook up to channel 1 and ground. And then it's got a little twist lock like BNC connectors. A lot of the aftermarket ones have. You can still use it with the tool. You would just use it on the voltage setting, not the pressure probe setting, because the scaling is not the same between them. So just be aware, you can plug in any of the pressure probes you can find out there. So when we do have pressure probes, pressure transducers as it were, what can we test? Well, we can test fluid pressures for sure. So things like fuel, transmission fluid. So when I'm shifting, check on the different shift solenoids when they operate. Does my transmission fluid pressure change? Hydraulic pressure too. Hydraulics on, say, equipment, or even maybe brake lines, depending on how you can adapt to that to make sure that your pressure is where it's needed to be. Now on hydraulics, for sure, if you're over 5,000 PSI, it won't really work because the max we can do is a 5,000 PSI on that transducer. But if you have up to 5,000 PSI, you would be able to check on that. And then fuel, we could do high pressure as well. Not really, not necessarily the safest way to go about it unless there's a way to tap into the line. But we do have a way to test any of those, right? And then, of course, gas pressures as well. So compression, that seems to be one of the more popular uses nowadays for using the pressure transducer. And we'll talk quite a bit about that a little bit later. And then exhaust back pressure as well, as we can measure the exhaust pressure, see if we have a blocked exhaust system, blocked cat, that sort of thing. We can see that with the transducer as well. So first off, we'll start with fuel pressure, and we'll show you how we would test fuel pressure by using a real world example. So we have this O2 Explorer here, and the problem was it is a no start after a PCM install. So the PCM was replaced at another shop. Gotta love when those happen, right? Somebody else did the work. I'm not really sure entirely what they did. They said they replaced the computer. Did they do anything else? It's always the way, right? And another shop does it. They can't get it right. So it ends up in your lap, right? So it was replaced at a different shop. The engine did start after a parameter reset, but a short time later, it wouldn't start again. So they needed to figure out why it wouldn't start, right? No start condition can be a lot of things. So the vehicle was checked for spark because, well, we need spark in order to start the car, right? We also need fuel. We also need compression. So we do have spark. That works. They also think, well, maybe the wrong PCM was installed in this thing. Maybe it plugs in, but maybe the programming's wrong or whatever. So then it won't allow the vehicle to, maybe the injectors aren't working. So next thing they said, well, spark is good. Let's check fuel. So they check fuel pressure with a manual gauge first, you know, the one, the usual analog gauge there. And when they would go to crank it over and not start, they noticed something. The needle was fluctuating wildly like this. It was going up and down, up and down, up and down as they cranked, kind of following the pulse of the engine, so to speak. So that's a little curious because it should just be kind of a straight, maybe a little bit of a drop, but not a lot of drop. So they said, well, let's get a visual on it. So after we're looking at the gauge, you want to get a good visual on the screen on your tool so we can go through and take a look with the pressure transducer. So they hooked up to the fuel line, tapped into the fuel line there. And you can see as we turn the key on, fuel pressure builds slowly as it should, up to a little over 60 PSI, which is normal pressure for this particular vehicle. It's a Ford Explorer, as I said. So a little over 60 PSI is where we want to be. And then cranking, watch what happens. So it goes from a little over 60 PSI down to like 20 PSI. And then up to a little over 40, and then down to 20 and 40 and 20 and back and forth, back and forth. You can see there's where that fluctuation was in the needle on the gauge. So there's a massive drop in pressure when we go try to crank this vehicle over. If I'm losing fuel pressure, maybe that's why it's not starting. So let's get a little bit deeper and see, let's hook up to an injector and see what's going on with the injector with the pressure at the same time and see how it goes. So in this example, we have the pressure on the yellow channel again, channel 1. The green is the fuel injector power voltage, and then the blue is the amp probe to make sure that that fuel injector is opening. And we can see when that fuel injector opens, that's exactly when my fuel pressure drops. And it is a big drop. It is from 60 to 30 in this case. So that is a huge drop every time, and it's not able to build up enough pressure because it's bleeding off too much when it fires. Now, why is it bleeding off so much pressure? If we look at the on time of that injector, it's 250 milliseconds. That's a quarter of a second on time. That is a crazy amount of on time at, say, normal temperatures, 60, 70 degrees outside at the time. That was far from normal. That's way more than it should be. So they said, well, that's awfully curious because that's not a good thing. There's a lot of codes in the vehicle as well. So they looked through and they ended up finding the DPFE sensor was shorted on the 5-volt reference circuit. So DPFE is the EGR differential pressure sensor. And it had shorted. When it was plugged in, the 5-volt reference circuit dropped to about half a volt, 0.4 of a volt. If you unplugged it, went back up to 5 volts. So it was shorted internally, pulling that voltage down to ground. So they replaced the sensor and they said, well, let's verify. Let's do the same test and verify that we don't have that same behavior anymore. So they hooked it up, and there's my pressure. And we see the pressure stays around 60, and then it drops down to maybe 50, and then it goes back up, builds its way back up. So there's where the injector closes, and then we see how it kind of builds its pressure back up until the next injector firing event happens. And then we are down to 36 milliseconds there. So that's more of a reasonable startup time. So if we think about what happened, the hypothesis is if it's shorted down, not quite 0 volts, so we got maybe half a volt going through the 5-volt reference system. Multiple other sensors are connected to that 5-volt reference system. So if it pulls the whole thing down, all those other sensors are going to read incorrectly. So for example, in this case, if the coolant temp sensor fails on the low side, then in this case be low temperature. So if I'm reading -30, -40 degrees out, what's my injector on time going to be? It's going to need to be longer, right? So the guess is that's what made that injector on time. It makes sense, right? If you think about how that 5-volt reference signal can be affected in that way. So that was just one way of seeing, well, there's a massive fuel pressure drop, and we're able to visualize that with the scope using the pressure transducer, right? So that's our fluid pressures. Transmission fluid, hydraulic fluid, it would all pretty much look the same and react the same. You just got to think about what it's doing when it's flowing as to the different things that are going on. But it's going to read just a line across the screen with whatever the pressure happens to be, and you can translate the pressure on the left there. Now let's look at exhaust pressure. So exhaust pressure, there is actually a quick test inside the tool. If you have a snap-on tool with a scope, inside the training and classes, I'll show you how to get to it a little bit later. But inside there is actually a test on exhaust back pressure. So it says back pressure can be checked using the tool along with a split lead adapter, or in the case of a 2-channel tool, we can use the other adapter, which connects the auxiliary port of the tool over 100 PSI pressure and vacuum transducer. We're going to hook the test leads up. Yellow goes to, in this case, the 100 PSI transducer. You could use 500 as well. Black to a no good ground. There are several ways to adapt transducers to measure exhaust back pressure. The easiest way is to remove the oxygen sensor from the exhaust system and install a back pressure adapter in its place, which is what we did in this case. We removed the rear O2 sensor on this car. Then you'll connect the exhaust back pressure adapter hose to the transducer, start and run the vehicle at idle while observing back pressure on the tool. Pressure should not exceed 1 PSI. So in this case, we see it's right around, little up and down, but around about 1 PSI. Increase engine speed to 2,000 RPM. It should not exceed 2 PSI. So a known good value, rule of thumb, for exhaust pressure, we should see no more than 1 PSI at an idle, no more than 2 PSI at 2,000 RPM, and that's a way to test. So in this case, since we use the back oxygen sensor, the rear O2 sensor, we're not really able to see anything that happens before that, right? So we can see if there's any blockage behind it, muffler blockage, resonator blockage, pipe crimped. You'll probably be able to see that with your eyes too. But for drivability purposes, we need to have an unrestricted exhaust. So in this case, we also added a restriction to the exhaust just to see what it would look like. So just to stick the hand over the tailpipe till it builds up enough pressure to push it off type thing. So we see it gets up to about 6 PSI on the back end. And we got about 1 PSI on this side. Now you'll also notice it is on a 10-second time base. So that is a long time. This is actually a graphing meter screen that comes up, and you're able to see individual kind of up and down with the pulses of the engine. It's a 4-cylinder engine, so you're just kind of pulsing up and down because the exhaust pulses are coming through, one after the other. They're coming through the exhaust. And then, as we said, it goes up, ramps up every time you put the hand over the exhaust. The pressure builds. And then when you release your hand, then the pressure goes down. So if they're at a blockage and I saw 5-6 PSI, I know I had a 5-6 PSI blockage. You could also do this in the front cat, right? Front oxygen sensor. In this vehicle, we couldn't quite get to it easy enough in the time allotted, so skipped over that part. But this is what it would look like. You'd be able to see the front end of the cat. And if you did both, you could do 2 channels, right? You could see your pressure going in, pressure going out, and see if there's a differential between the pressure going in and the pressure going out. All right, being able to see that difference, visualize that. You pull out the front O2 sensor, pull out the rear O2 sensor, let it idle, and see what happens. So a couple different tricks there we can use for exhaust. Now, how about relative compression? This is another test that we can do if you're here early on, before we started, we talked about how to do a relative compression test with a scanner on a Ford. There are some vehicles that'll do that. Or we can also check relative compression using a low amps probe, but sometimes that's not practical. And then other times we can use relative compression doing a voltage drop as well, but sometimes that's not necessarily what we're looking for. So in this case, the vehicles will be able to do this easier than others because we need to be able to access a vacuum line. And not every vehicle has a good vacuum line that'll see the change in pressure. And we would want to use a differential pressure sensor ideally because it'll react faster in order to get the ups and downs. But here's an example on a known good vehicle. This is cranking vacuum. All right, so we can see it goes up and down, positive, negative, either side is zero, just kind of ups and downs, comes and goes, fairly even. It's the way it should be, right? We have compression, we have vacuum, and it's fairly even on either side. So you're going to see the different pulses. And of course, they added a channel 2 to know where cylinder 1 is. So they've just put this on cylinder 1 spark plug, and they can see there's cylinder 1, 2, 3, 4, 5, 6, 1 again, or whatever the firing order is anyways. But it's a 6-cylinder vehicle. And then cylinder 1 again. So that's a known good. I bring up the known good because this compares to this known bad vehicle that we're looking at. So this is on a Jeep, and it was a 6-cylinder Jeep. As we see, there's cylinder 1 there with our spark plug firing there, spark plug firing there. And then we overlaid the numbers. So we have 1, 6, 5, 4, 3, 2 is the firing order. That goes back to number 1. So this is a vehicle doing a relative compression test with a pressure transducer, and we can see the odd number cylinders are lower than the even number cylinders. So what was the problem with this vehicle? What actually happened on this is we had a large pressure pulse on the exhaust stroke here, and a low vacuum pull coming in on my compression stroke. So this low compression on these was due to a clogged cat on one side. So it was a V6. So that odd number side had a clogged catalytic converter, so the exhaust wasn't able to get out fast enough. So on my exhaust stroke is going to be over here, and that, as we can see, it rises up and we get a pressure pulse right there on the exhaust side. So this just lets us know we have a problem relative to either side. And yes, you more than likely would have been able to see this with an amp probe as well, because it would have taken a different amount of amperage to turn that even side versus the odd side. Right, so we would have been able to see that in a amp probe as well. But this gives you a very big visual as to the different sides, and we'll see why in a second when we get to another test that they did on this. But that was a big problem on that engine. It had a bad cat. Now let's look at cranking compression. So we talked about relative compression, which isn't as easy to do. Cranking compression, we can do that on a single cylinder if we'd like. And we put a compression adapter in there. We put the pressure transducer in there. We somehow clear flood or pull a fuel pump fuse or a relay or something like that. Disable the fuel system so it doesn't fire. And then we crank it over. Running the cranking compression, we can see how does it look? How much compression is it giving me? How much pressure do I see? So here's just an example zoomed out. And this is on one cylinder. We can see how it just cranks, and they're all going to be even because it's one cylinder. But we can see what the pressure is. All right, so we can take a look at what the pressure is. This is zoomed in a little bit closer, and we can see 113 psi right there at the top of my cranking waveform there. So you crank it over, you go back, and you look. This way we can tell compression cylinder to cylinder and see what the difference is. And now we have running compression. So running compression seems to be the most popular test to do with a pressure transducer, and a lot of mystery around it, I guess. And there's a lot of other classes on how to analyze these waveforms. We're not going to go way far in depth because we don't have a ton of time, but we'll do at least give you a good overview of what you're looking for here inside a running compression test with a transducer. So here's an example waveform that we see, and this shows all 4 strokes of the engine here. So it's going to start with my compression. So my compression builds, compression builds. And then the spark plug fires, you know, a little bit before it gets to top dead center, but there's top dead center. And then it'll expand and go down, right? So we have down there, it goes down to bottom dead center down here. And then we have our exhaust phase, right? So I'll have our exhaust phase there. There's my exhaust. And then my intake will start. So that's about in there. And then my compression phase starts again, back to top dead center. So that's 720 degrees of engine rotation from there to there. So we can see this is a known good. This is a good done on my car last week on a 500 PSI transducer. So we can see we get a good looking picture with that. And we can see ups and downs. And I'm going to show you a couple different ways we can analyze this a little bit more. But what if it was bad? All right, so this is a good one. What if we had a car that had bad compression on a cylinder? So here's an example here, an 08 Saab, must have been a 9.7 because it's 5.3 liter. So this is no compression on cylinder 6. So this is the same type of thing. Pressure transducer in there. We see it that barely builds over 0 at all. And it's just there's no compression. We still get to see it pumping, but it's not building any pressure in the cylinder. So that had a problem inside the cylinder where it wasn't able to build compression at all. Comparing this to the companion cylinder next to it, or this, you know, whatever, this neighbor cylinder 8. So this is cylinder 6, no compression on that cylinder, dead hole. Cylinder 8 looked like this, using the same transducer and the same setup. So we can see goes up, comes down, exhaust, intake, etc., etc. So it goes up and down, and that is a normal looking cylinder. Now this is a good lesson, not just on, hey, what does bad look like, but don't necessarily test the bad one first and think, well, that pattern doesn't look right. Well, why doesn't the pattern look right? Because it's not, because there's a problem with that cylinder, right? So always test known goods. Always a good idea or a good practice to collect a bunch of known goods. So we can see, oh, what is normal on this engine before it breaks. So there's a known good on that. And then one more, or actually I got a couple more, but this one is on that Jeep. The Jeep with the clogged cat. So first off, they see the relative compression test, one side's lower than the other. That's curious. So they decided to go into one of the cylinders internally running. This is on cylinder 1, I guess. And you can see that exhaust stroke pressure is getting higher and higher as it goes. And actually it's over 0 PSI. So that's not good either. Because if our exhaust is flowing the way it should, we should not have any excess pressure in the engine when the exhaust is leaving through the exhaust valves and going out the back of the tailpipe. As we can see, it's above 0 and it's building. So that means it's building up. So as soon as it's hitting that clog, it's backing up, backing up, backing up, and it's increasing the amount of pressure in the system overall. Now, it's not a ton, but it's enough that it's going to cause a drivability problem. If I can't get all my exhaust out, I can't get as large a volume of air in because it's being taken up by exhaust. And it's not going to run very well because it's got a lot of exhaust gases in there still. So I just thought that was kind of a neat little visual, very plain to see as long as you know what you're looking for, where there's an issue. So I can see the exhaust pressure ramping up. And then one more before we talk about live stuff on the tool. This is one, this is on my car as well. The other day decided, well, let's take the compression and let's overlay the ignition and the fuel injector on the same cylinder. Now, this is kind of interesting because you don't always think about, well, you know, the injector is going to fire before the ignition, right? It is going to fire before the ignition. This is not a direct injection vehicle. It's a multi-port injection. So if we think about it, that injector has to fire before the intake stroke because otherwise that air is not going to come in with it. So it fires, and then we see the intake stroke starts right around here, and there's a little bit of valve overlap there. And notice how the pressure changes, the reading changes. On my exhaust, I got this with my swirl and my pulses, but over here, once I have more air being introduced and I have fuel being introduced, the pressure changes a little bit. I just thought that was really interesting. How you could see that detail. The pressure changes. And then we have our intake stroke and our compression. Now also notice this is the ignition event. So that's going to be over here somewhere if I follow that all the way up. And of course, it's before top dead center, right? Normal, idle. It's going to be a little bit before top dead center in that case. And we're going to walk through this pattern and take a look at the differences and how far apart these are, and look at the 4 phases of our running as well. All right, so that is our overview. How are we going to hook up? How are we going to test? What should we be seeing when we do this? Now let's look at a couple patterns live. So I got a couple questions coming in on Zoom. As I said, I'll get to those at the end. I got a couple coming in on YouTube as well. So if you do have any questions on Zoom, hit that Q&A button, type your question in, and on YouTube, please make sure you use that live chat function in order to ask your question as well. So first off, I want to show you this tool. I don't want that though. I'll close this down. So there is a tool that you can download on a Windows 10 machine that is called Pressure Waveform Overlay. So you can only get it from the Windows Store. So you have to go to the Windows Store on your Windows 10 computer, type in Pressure Waveform Overlays, and it's a little app that downloads. It's not like a traditional exe file or whatever you might be used to. So you can't install it on just any Windows capable computer. It'd be nice if it was, but it's not. So it's only available through the Windows Store. And the nice thing about it is it's free. That's one nice thing. It's free. It's for me. It's what I always say. But what you can do is you can load a waveform. So you take a screenshot of your screen. So let me go find one here. I think this one is good. There we go. Actually, that's not the one I'm looking for. I'm looking for the other one. No. It's hard to see with Windows, right? So cranking. I think that's the one. There we go. That's the one. All right. So it's best practice to have 2 of these compression humps, the top dead center on the screen. So that way I can see one full set of the 4 strokes, right? So now, once I have this up, I can turn on these rulers. And the rulers tell me, if I line up the first line with the first top dead center, and the last line at 720 degrees with the last top dead center, we can see my 4 cycles. So here's my expansion right here, comes down. Then we get into the exhaust phase where the exhaust valves open. And then we get into the intake phase where we draw in the air and fuel. And then we get into our compression phase up. And then once again, it goes back down to expansion. So we can see where those 4 lie. Now, as I said, a little more than what we get into here, but there are ways you can look and see, okay, how many degrees is different and where's my valve overlap? There is an automated valve overlap overlay you can add in here too, right here, which is going to tell you, well, here's 39 degrees before bottom center, and here's 9 degrees after top center, and all that. And every manufacturer is going to be a little bit different, and the camshaft's profile is going to be a little bit different. So you can actually move these around as well if you want to drag them around. But that's just a couple examples of things you can do really quick and understand what's going on with each of these 4 strokes on the engine. So I thought that was a neat little tool that you can use. Like I said, just take a screenshot, any JPEG, bitmap, what have you will work. You can overlay that and it shows you where the 4 strokes go. Okay. So that's one thing. Get out of that. Now let's take a look on the tool itself. So if I go onto my Zeus in this case, there's a couple things I want to talk about. So first off, I want to talk about in guided component test. So if you have a tool, a snap-on tool with a guided component test function in there, so Zeus, Triton, Modus, Varus, Vantage, Verdict, they will have classes. So go into guided component test, go into North America in this case. And if you have 21.4 software, which is the current version, classes will be on the top. On older software, the classes will be down here at the bottom. So they just moved where the button is. So in this case, we got classes. Now, if I go into powered user tests first, and I go to transducer tests, we can see there is an exhaust back pressure test. There's also AT line pressure shift solenoid, line pressure. I wanted to do line, AT line pressure, fuel pressure, fuel pump current, etc. But here's my back pressure test. And it tells you hook up to the exhaust, like we said, hook up the transducer, you hit view meter. It's going to automatically set the voltage range, automatically set the time. It's also going to ask you if I wish to calibrate the probe. Now I don't have the probe plugged in, so I'm just going to say no, but it automatically calibrates when it sets up as well. So you want to make sure you have it open to atmospheric pressure at the time to calibrate it. So that's a real easy way to do your exhaust pressure. It's going to set it all up for you. If I back out of that and go to my how-to, under how-to, if I need a little bit more of a refresher on my running compression, there is a 10-minute running compression waveform class in here. So pressure transducer can be used to monitor in-cylinder dynamic pressures with the engine while the engine is running. This example shows a pressure transducer calibrated to 500 psi, fitted to a spark ignition operating at idle speed, approximately 800 RPM. We can see peak compression pressure, cylinder sealing, exhaust valve opening period, and inlet valve opening period in there. So fit the pressure transducer, remove the spark plug from the cylinder to be tested, use a suitable adapter to thread into the spark plug well, fit the spark plug to the high tension lead or ignition coil and connect the spark plug to a known good ground. You want to make sure the spark plug is sparking. Failure to do this could damage the ignition system. Sensitive electronic circuits can be damaged by a back electromotive force caused by an open circuit. So we want to make sure that spark plug is still sparking. Electronically disconnect the fuel injector from the cylinder being tested. Failure to do so will result in fuel entering the exhaust, where it can be combusted within the cat, resulting in thermal stress and damage of the converter. Image below shows a waveform captured over a time base of 200 milliseconds, which is a good place to start. Engine speed of 800 RPM. We can see the entire engine cycle. The 4 strokes are easily identified. 2 cursors are used to display 1 cycle from top dead center on the compression stroke to the following compression event. A smooth but sharp increase in cylinder pressure must be observed. Maximum pressure will be observed at top dead center. This is because the smallest volume exists in the cylinder due to the engine valves closed and the piston at its uppermost of travel. Normally, an ignition event would take place at this point, but with the absence of the spark plug, the expected combustion pressure will be absent. As the piston moves down on the power stroke, the volume of the cylinder increases. Both inlet and exhaust valves are closed and depression is created, so we're going to have a vacuum. A steady drop off in pressure down to a negative pressure indicates good cylinder sealing. So I need to see that negative, that vacuum hump down here at the bottom. I need to make sure it goes down pretty much as it goes down over here, because that tells us we have good sealing on the engine. Let's see, the reduction in cylinder pressure should be similar to the increase in pressure observed on the compression stroke, like I just said. This indicates good mechanical condition of the cylinder. When the exhaust valve opens, the piston moves up the cylinder on the exhaust stroke. The pressure in the cylinder should increase up to atmospheric pressure. So in this case, we're talking on this pressure probe, since we calibrated it is relative. So atmospheric pressure should be 0 in this case. So it's relative to whatever we calibrated it to. Towards the end of the exhaust stroke, the inlet valve will open, and after a short valve overlap period, a depression will be created within the cylinder as the piston moves down the cylinder in the inlet stroke. Pressure observed on the inlet stroke should be similar to the pressure observed at the end of the power stroke. And then there we go. So there is that. And then if I hit view meter, if I had it hooked up, it would ask me to calibrate. And then it's going to set that up for me at 200 milliseconds and then up to 250 PSI at the top there. So 2 easy setups. All you got to do is hook it up to the car right inside the guided component test. All right. So one more thing. Let's look at, oops, not that one. Let's look at my data. And I'm going to pull up this one right here. So this is the running compression waveform with the coil, with the injector. Now, in order to capture this and get it to look the way it did, I did it the way you're not supposed to do. I had the injector plugged in for like a second or two while I let it run for like a quick second and captured it, just so I could get a good injector pattern, because otherwise it was unplugged and it wasn't very good. It wasn't very easy to see, let's put it that way. You got a little bit of a control blip, but it wasn't quite as obvious. So as we can see, it goes up, comes down, exhaust, comes down, compression. So let's see, pull that, change my channels here a little bit. There we go. So you can see that a little bit better. Now the end of this waveform is going to be where my spark plug fired. So I was checking on the dwell side there, so on the primary side. So we should be able to see that. So let's turn on our cursors and do a couple of measurements. So in lieu of having that other software that I showed you, you can still do this on the tool. And what we want to do first is we want to take our cursors, put one there, put one there. That'll capture 720 degrees in our revolution. And in this case, it takes 144.51 milliseconds for one revolution. So if I know I got 720 degrees in here, I'm going to take my 144.51, divide that by 720 degrees. Gives me 0.2 milliseconds per degree. Okay. So if I go over here, put that there, and I go over here and put that there, I can see how many degrees before top dead center my spark plug fires. So 4.17. So it's 4.17 times 0.2. Nope, wrong way, divide. 4.17 divided by 0.2. There we go. 20 degrees before top dead center. 20.85 degrees before top dead center is when this cylinder fires. What else can we tell? Well, if it's 0.2 and I want to find 180 degrees, go back here. So 0.2 times 180, 36. So I should have 36 milliseconds per stroke. So let's see, that should be somewhere around about here. There's 36. So that's my expansion stroke. And then another 36 or so. Once again, depending on valve overlap and all that good stuff. That's my exhaust stroke. Then another 36 or so. Close enough. There's my intake stroke. And then my compression stroke should be another 36 right there. All right, so every 36 milliseconds is one of those strokes. So how far after this guy does my injector fire? We'll go somewhere right around there because we know it doesn't fire at the very beginning. Close enough. 59, call it 60 milliseconds. So 300 degrees after, so almost on the other side, right? So almost on the top dead center the second time. So actually, by the time it fires, it's going to hit top dead center on the exhaust stroke, and then you'll see how it pulls in there. But I also thought that was really neat, how we can see the waveform change from exhaust to intake with the fuel. I thought that was kind of cool, right? All right. So that is my rundown on pressure transducers. And with that, that is our time here today. So make sure you tune in for new diagnostic content every week. We will be premiering a new video every Wednesday at 7 p.m. UK time. So make sure you check it out on the YouTube channel. If you're watching, well, of course, you would be watching this on YouTube, but make sure you subscribe, thumbs up, ring the little notification bell so you know anytime we post new content. And it's youtube.com/SnapOnDiagnosticsUK. With that, time for questions. If you have any questions, just feel free. Once again, if you're watching this on a premiere, just leave it in the live chat and we'll answer those. Otherwise, leave a comment under the video and we will get to those as we monitor those comments as well. So I'd like to thank you for taking a little bit of time out of your day to learning a little bit more about how you might be able to be more efficient at diagnosing vehicles using some of the information that we've given you today. Hopefully we'll see you next week. Hopefully you can watch and see you on any of our other videos. Have a good week, have a good night, and take care.